Assalamu alaikum Physics 20. So we're going to talk about work and energy. I don't want to waste too much time with the long answer, so let's get right to work. Alright, that was a bad joke, but in all seriousness, work is actually a very important part of physics. When we talk about work, we're not talking about the countless hours that you spend doing some sort of homework or helping your parents. We're talking about the force that's applied over a set distance. Now, the key word here is the force that's applied, because it's really only an applied force that does any kind of work along an object. So we can essentially sum up work as something that describes making an object move or making an object stop. So work isn't negative, but you can do negative work. And what we mean by that is, if I do work in the positive direction, meaning in the direction that the object is moving in, well, we would say that that's the work that's derived from the applied force. And that force would be in the same direction that the object is moving. However, if we're talking about the work that is needed to be done on an object in order for it to stop, well, then that would be the work due to friction. And while work itself isn't negative, you're doing negative work. Now, work can also be understood as the change in any kind of energy that an object experiences, and that makes sense because as you change your distance from becoming moved, you would also have some sort of energy change. So we can think about work as a change of potential energy, or we can think about a work being done on an object as a change of kinetic energy. And so we got two working formulas. Get it? Two working formulas. So I apologize for the dad jokes, but let's play a game just so that we can conceptually understand this of what kind of work is being done on the object. As my son Dean pulls the Lego box across the floor, what kind of work is being done? While at the same time, what kind of work is being done on the box to stop him from moving it? What kind of work is being done when he holds the book against the wall? Remember, the book is not moving. Lastly, what kind of work is being done when a mischievous little brother comes and pushes his older brother from behind while reading a book? For scenario 1A, remember that the box is going in the same direction as the motion. And so we're thinking about our force applied would be this way. Everything else would cancel out. And so we can say that since the object is moving in a direction that is equal to the force applied, we would call this positive work. Now, for the second portion of this object, remember that he's been doing this on carpet. So, carpet, which is a pretty rough surface, is going to provide a lot of friction. And so while there is positive work being done on the object, friction creates negative work that is done on the object. And so in both the same instance, we have both positive and... Now for the second scenario, if you said no work is being done, then you would have been correct. Now this is weird to say because you're thinking, well, isn't he holding it up with the force with the normal force that is at least equal to gravity? Yes, but remember that work is equal to force times distance. And if there's no distance, then there's no work. So whenever an object is held, and we're going to write this here, if an object is held, the work is 0. Now for the third scenario, as you might have guessed, we could say that in general there's positive work being done. As the older brother is shoved, he moves into the direction that he's being shoved in, which means that the applied forces would have overcome the frictional forces. So, with that being said, what is work measured in? In physics, we love to do calculations, and for sure we're going to jump right to calculations soon enough, but work is measured in joules, which is short form for newtons times meters, and that's the force applied in newtons and the distance in meters that the object gets pushed or prevented from pushing. So with no further ado, let's get to calculation. So when it comes to us working with formulas, there are generally two that we resort to when calculating work. And the first one is work is equal to force times distance. Remember that your work will be in joules, your force is in newtons, and your distance is in meters. Now, this force over here, it's an applied force. And so we're only interested in forces that are in the direction of motion. So we're going to write in direction of motion. Now, the only other time it won't be the applied force would be when it's doing negative work, and that would be due to the force of friction, and then once again multiplied by the distance. So we have, when there's a force applied and there's a distance given, we can calculate the work. Another common work formula is when we use work is equal to a change in energy. And so this change in energy, it could be potential energy, more specifically gravitational potential, in the form of mg delta h, or it could be in the form of kinetic energy, which is given by the equation half mv squared. But either way, we're looking for a change in energy, and we should conclude from what we've seen before that work is equal to 0 when there's no movement, and that would be vertical or horizontal. It doesn't matter which one. So when there's no movement of the object at all, then work is always going to be 0. So whether it's staying still, whether it's being held, work is going to be 0. The first problem reads as a 5.0 kilogram steel plate is being held up at a height of 3 meters. What's the work done on the plate? So the key word is held. And if it's being held, that means that there's no movement. And what did we say about when there's no movement? Well, if the D is 0, then more importantly, the work is 0. And so the work done on the plate is 0 joules. Now for this next question, a 4 kilogram box is pushed along horizontally with a force of 40 newtons. Okay, so that's important. If it's pushed along with a force of 40 newtons, then that would be our F applied. So we would write here, force applied is equal to 40.0 newtons. If it moves 1.2 meters across the surface, so this is our D, how much work was done on the object? Work equals question mark. Okay, so one thing I want to mention is that the mass here, where it says 4.0 kilograms, because all we need is the force applied, we're not really interested in the net force. We don't need this mass for now. Now, there are other times when it comes to friction, for example, as the force that provides or that does work on the object, then we're going to take that mass into account. But in this case, we don't need to, so we're just going to go work is equal to force times distance, which is then going to be equal to, and we expand this properly here, that'd be equal to 40.0 newtons multiplied by 1.2. And then finally, you plug that into your calculator, and when we do 40 multiplied by 1.2, we get a work being done of 48 joules. Here's a little bit more of a complicated example. A 3 kilogram box is pushed along a surface at constant velocity. If it moves 2 meters across the surface, how much work was done on the box? The coefficient of friction between the surface and the box is 0.19. So, a couple of things here that are important to note. One is that if we have constant speed or velocity, well, that means that the acceleration is equal to 0. And if the acceleration is equal to 0, then that means that our F net, I'll write that a little bit better here, our F net is also equal to 0. So this box is moving horizontally, and according to our previous scenarios, when we have an object moving horizontally, then our F net equation is going to be F net is equal to F app minus force of friction. Now remember, what we're really interested in here is the F app over here. Now if the F net is 0, then we could just simply plug in 0 into our F net formula, and we have F app minus, and remember that the friction formula is mu Fn. Now the Fn, if it's a horizontal surface, it's equal to Fg. So what we could do is, we can write 0 is equal to F app minus mu mg. And when we continue to write this down, that would be equal to F app, which is equal to, we have a coefficient of friction given in the problem of 0.19, so we're going to do that here. We're going to go 0.19. We have a mass given of 3.0, so we're going to go 3.0 multiplied by 9.81. When we plug this into the calculator, the force of friction that we get is equal to 5.5917, that'd be newtons. And so to isolate for our force applied, we just move this over to the other side, and we end up getting a value of positive 5.5917 newtons, equal to the force applied. Now that we have the force applied, we can then go plug in that force applied into our work formula, which is going to be W equals to F times D. And the force applied is going to be 5.5917 newtons multiplied by 2.0 meters. And when we plug this into our calculator, we get a value of about 11.18 joules. And that would be the work done on the box. Okay, so for our final example, which is a little bit more complicated, we're dealing with two-dimensional forces here. It reads, a 50 kilogram fruit box is pulled 11 meters along a horizontal surface by a rope. If the rope makes an angle of 35 degrees from the horizontal, and the tension in the rope is 90 newtons. How much work is done on the box? So, there's a couple of things here that we have to think about. Remember that when it comes to the applied force is only in the direction that the box or the object is moving in. So when we draw a free body diagram like follows, our normal force and our force of gravity are equal. There's presumably a friction force. And then at an angle of roughly 35 degrees from the horizontal, we have a tension force that is pulling the box. Now, remember that what we want is the horizontal force because the box is being pulled to the side as that arrow shows. And so 90 newtons is not going to be what we plug in because that is not going in the x direction like the box as mentioned here is going. And it's the x direction that the force applied is in. So the force of interest is the adjacent side of that triangle. And so we're going to redraw this triangle over here. 90 newtons as the hypotenuse. It's 35 degrees from the horizontal. And the force of interest is this blue dotted line over here, which is in the x direction, which would be our F applied. From the angle, the reference angle of 35 degrees, our F applied is the adjacent side. And we have the hypotenuse given. So the appropriate formula to use would be the cosine trig ratio. And so our F applied is equal to 90 newtons of tension multiplied by the cos 35 degrees. And that would give us the adjacent side. Now what I'm going to do is plug this whole entire formula directly into the force times distance formula for work. And that'll give us work equals 90 newtons cos 35 as the applied force multiplied by the distance, which is about 11 meters. And when we plug this into our calculator, we end up getting a work value of about 811 joules. And that is the final work that was done on the box. So now that we have 4 example problems, I need you guys to get to work. And by that, of course, I mean practice. Let me know if there are any questions.